Hello everyone, today we are going to discuss about boundary conditions, and before understanding these boundary conditions, let's differentiate initial value problems and boundary value problems. Now, initial value problems generally refers or generally is based on time, whereas the boundary value problem is based on position. So what I mean to say is, for example, if we have let's suppose a problem, then if we define the conditions or constraints on the basis of time. For example, a t equals 0 and a t equals, let's say, 2 seconds. Now, in such case, this kind of problems is called initial value problems or IVP. If and in the same way, if we define conditions on the basis of position rather than time, then with, for example, let x equals 0 and x equals suppose 2 meter. So if we are talking about a rod, then at x equals 0 means at the first end, and x equals 2 means the last end if this uh, rod has a length of 2 meter. So in this way, if we define some position, then it is called boundary value problem, or in abbreviation BVP. The existence and uniqueness theorem, or the properties of initial value problems, are well understood. But when we talk about the boundary value problems, the existence and uniqueness solution are not well defined and are a little bit more complicated than that of the initial value problems. Now let's see some of boundary value problems, and let's see how to find the solutions of them. But before doing that, let's see how do we find solution to any kind of boundary. Let's see these three boundary value problems. So the all boundary conditions are second order derivatives, and if you see the initial condition, then it is same, and but the sorry, it is one. Okay, that's one. So the second conditions are different for every problem here. So let's see how to find out the solutions of these boundary value problems. Okay, so let's try to find out the solution of first equation. Y double dash equals y. So the solution of this can be found by y double dash minus y equals 0, and this can be written as, let's suppose, let the solution of y be e to the power mx. That gives us y dash equals m e mx. Y double dash equals m squared e to the power mx. And if we substitute these, then we get m squared e mx minus e mx equals 0. And if I take e to the power mx equals is common, then we get this equation. Now, if here we can see this cannot be 0, and so this must be 0. That means m squared minus 1 equals 0. That gives us solutions m equals plus minus 1. Now, after finding this m equals plus minus 1, these are distinct and real roots. That's why we can say the solution of this yx, because it's a boundary problem, yx equals uh, a e to the power ix, I think e to the power x plus b to the power minus x. This is the solution. Sorry, it's not m. So if it goes there, then it is plus 1, right? So we get this value. I want to apologize for a thing that I did here. Actually, I had to write minus to make these all questions same, the differential equation same, but the conditions should be different. So that means we have a plus sign here, and a plus sign, and a plus sign, and a plus sign that gives us, plus minus 1i, and that gives us solution a cos of x plus b sin of x. I'm so sorry for that terrible mistake that I did. So this is what the solution is. Now we know that since the three differential equations are same, it means all of them have a solution which looks like this. Okay. Now we have to find out how does conditions change this. So let's apply the first. Let's apply these conditions. So let's say at uh, x equals 0. At x equals 0, the whole thing is 0. So 0 equals a cos 0 is 1 plus b sin 0 is 0. So therefore we get a equals 0. Now let's check the second condition, x equals pi. Now at x equals pi, uh, x equals pi, a is already 0, that means b is sine pi. Now this is equals to 0 equals b sine 0. So sine pi is 0. It means that b is not equals to 0. That means b can be anything. Okay, so it doesn't matter. Either what the value of either what the value of b is, because for any value of b, the the solution is there. The solution exists. That's why we can say from these two boundary conditions we have found out a equals 0 and b can be anything. Let's say this to be bn, and for these solution exists. Now let's check the second boundary condition, and the first in the second boundary condition, the first condition is same. Let's check the second condition. Now here the second condition is it x equals pi by 2. So if x equals pi by 2, y of pi by 2 equals, now a is already 0, so b sine of pi by 2, right? Now sine of pi by 2, now this is equals to 0. 0 equals b sine of pi by 2. Now this sine of pi by 2 is 1, so this cannot be 0, so b equals 0. So here b is equals to 0. So at this condition, b has only one solution, and that is 0. Again, let's check. So it is for first condition, and for second condition b equals 0. And let's check the third condition, that is pi equals pi, and y of pi equals a is already 0, so b of sine pi, and this is 0 equals b. So this is 1, right? This is 1 equals b sine of pi. Now, okay, so let's understand this one. So we have sine of pi equals sine of pi, b times sine of pi equals 1. Now, what do we what can we do here? So if you see here, sine pi is 0, sine pi is 0, and 0 times b is also 0. It means 1 equals 0. Now this is a condition that means no solution. So we have got three conditions from the three separate boundaries, or three different boundaries. First one is, if we see here, we found out it has infinitely many solutions. Infinitely many solutions. If you see this boundary conditions, this set of boundary conditions, then we found out that it has only one solution, and that is equal to 0. And the third one here is, this says that it has no solution at all. It has no solution at all. So in this way, we can find out the solution of various boundaries. I'm sorry if I'm being a little bit confused here, because it's also my first time to explain something like this. So thank you for watching this. Let's move on, and let's understand some of other boundary conditions and problems. Okay, now let's discuss about some of standard boundary value problems, and among them the first one is Dirichlet boundary value problem. So the question is to find out all the solutions to the following boundary value problem. Now you may notice we have uh, second order ordinary differential equation, and we have two boundary conditions. Okay, now the two boundary conditions, you can see there is no differentiation of those boundary conditions. Okay, you should notice that. Okay, now let's see how to solve this. Now let's suppose, now we have to find out all the solutions, right? It means this lambda here can be 0, can be negative, or can be positive, right? So let's take all those three cases one by one. Solution is, let's suppose lambda is equals to 0. Now if lambda is equals to 0, it means our differential equation becomes y dash y double dash equals 0. Okay. Now the solution of this can be written as the solution of such kind of differential equation where the differentiation second differentiation is 0 can be a linear function, because if we see if we take any linear function, then the second derivative is 0, right? So we can assume that this is to be a solution. Okay, so let's say the solution is yx equals ax plus b. Okay, so this is a solution. Now, this means that yx is equals to something, just a naught is also a solution. Okay, now such kind of solutions are called steady state solutions, or steady state or constant solutions. Constant solutions, because if we draw these solutions, then it gives just a single line. For example, if suppose yx is equal to 0, so yx equals a naught, right? So this is a steady state solution or constant solution that we get. So these can be also solution of that differential equation, or if we have some linear functions, that can be also a solution of that differential equation. Now that is the solution for when lambda is equal to 0. Now let's see if lambda is not equal to 0, but rather lambda is smaller than 0. That means, sorry, lambda is equal to omega is equal to omega squared. It means it's always positive. It means if what so what are the solutions that we get if lambda is greater than 0 or always positive? Okay, it means always positive. If it is always positive, lambda is always positive means the solution here, if we take this lambda y to the other hand side, then it becomes minus. So this gives us 0. Okay, now if we do so, then we get solutions yx equals c1 e to the power I e to the power I omega, so e to the power omega x plus c to e to the power minus omega x. So these are the solutions of the Chipstead equation. Now let's apply those boundary conditions here. So right, let's take y equals, so x equals x equals what? At x equals 0. At x equals 0, this whole thing becomes 0 equals c1 plus c2, right? Because everything becomes this becomes 1, this becomes 1, the result of which we get this. Then after, if x is equals to pi, the thing is 0, it means c1 e to the power pi x, sorry, omega pi plus c2 e to the power minus omega pi. Okay, so we get the solution. This does not make sense, right? Because how do we find the value of such exponential? So that's why I'm going to introduce something now. That is the relation between exponentials and the trigonometric functions. So if we have something like uh, e to the power ix plus e to the power minus ix by 2, then we can write it as cos of x, right? Cos of x. And if we have something like e to the power minus x plus x minus e to the power minus x by 2i, we can write it as sin x. Similarly, if we remove these imaginary terms and write the real terms, then we get cos of hx hyperbolic functions like this. Okay, so we can replace those exponentials with these values, and as a result of which we get the value to be a cos of hx cos of h omega x pi plus b sin h omega pi equals 0. Okay, now from here, if we consider, okay, we have considered a and b, so let's consider these to be a and b. uh, a and b. Okay, now from here we get a equals minus b, and if I put minus b here, and if I take common, I get value of b is equals to 0, because this whole thing cannot be 0. It means that we get b equals 0 from here. After that, we can, okay, let's take a condition where lambda is always positive. So if lambda is always positive, why not let it to be something, the square of something? So if we do so, we can write lambda is equals to omega square, which is always positive. Now if lambda is always positive, then in this differential equation, if we take lambda to the left hand side, then it becomes minus. So as a result of which we get the solution this. Now one thing we should understand here is, since we are talking about boundaries, and we are talking about and if we have some exponential functions like that, it will be very hard for us to find out any kind of solution if the x is other than 0. So that's why we can introduce the interrelationship. We can exploit some interrelationship between exponentials and trigonometric functions to make our work easier. Okay, so these are some of the relations that are very popular in our interrelation between exponentials and uh, trigonometric functions. So if we have imaginary terms, we get cos and sine, and we have non-imaginary terms, that are real terms, then we get hyperbolic functions like this. Okay, so if we do so, we get the solution is a cos of hx plus b sine of hx. Now let's use the boundaries. This is the solution. Okay. Now let's so what is it? Okay, so let x equals 0. At x equals 0, we get a we get 0 equals cos 0 is, what is cos 0? Cos 0 is 1. That means it's 1. Okay, let's not write it here. Let's write a times 1 plus b times 0. That means a is equal to 0. A is equal to 0. Now again, let's use the second boundary condition, that is pi is equals to a. A is already 0, so b sine of h pi. Now what is the value of sine h pi? Now we know sine. Okay. Oh, sorry for that. We need to write omega x because we have omega x here. Omega x. So we can say sine of omega pi, right? Now, at what condition this whole term is equals to 0? Now let's suppose that b is equals to 0, because I don't think sine of h omega pi is ever going to be 0. That's why we get b equals. That's why we get b equals 0. This means that we have no we have zero solution only. So if we write these values in this solution, then we get zero solution. Y of x equals 0. Okay, this is the first solution. So this is the third solution. First, second, which are of lambda equals 0 case, and the second one is the whole solution is 0. That is 0 solution. Now let's talk about the third case when lambda is smaller than 0. That means it's negative. So if lambda is negative, then we can say lambda equals omega square is 0. Is smaller than 0, right? Now let's then our solution would be so it's negative, so it comes to the left hand side and it becomes positive. It means y double dash plus omega square y equals 0. That gives the solution. Solutions m equals plus minus I omega. As a result, we get solutions like solutions y of x equals a cos of omega x plus b sine of omega x. If we do so, and if we add, and if we write the boundaries at x equals 0, whole thing is 0, and sine 0 is 0, sine 0 is 0. So we get a, wait a second, okay, so this is already 0, this is 0, so a becomes 0, and it x equals pi. Again, the value is 0, is equals to, is already 0, equals b sine of omega pi. Now, at what condition these uh, these these are equals? These are equal to each other. And the thing is, if we so pi, right? This is equal to, so if b is not equals to 0, if b is not equals to 0, then sine of the omega pi, sine of omega pi must be equals to 0. That means sine of pi must be equals to n pi, and that means that omega is equals to n. That means omega equals to n. And if we write that in the solution, we get y of x equals b sine of nx. This is the solution. Okay. Now let's combine all these solutions and let's write the all solutions of boundary value problems, or set of solutions. Now, so how do we write it? So now lambda. Okay, how do we write all the values of lambda? Okay, so we have a solution which is this one, yx equals b sine of nx, y of x equals ax plus b, y of x equals 0, and y of which is n squared, and the and one case where b is equal to 0 and a equals to a naught, the case solution is a naught. So these are the set of solutions. These are all solutions of the boundary value problem given by that, or the Dirichlet boundary value problems. Okay, now this will find its application in upcoming lectures or upcoming series, which are partial value problems, heat equations, wave equations, and Laplace equations. If we try to visualize this boundary condition, we may visualize it as, so let's suppose we have, so it says it's a boundary condition at x equals 0 and x equals pi, and it says that at x equals 0, solution is 0, and again at y pi equals 0, it means this is also 0 at this point. It means the solution may be whatever there in between these x and pi, x is 0 and pi, but inside it, it must be a solution. It can be any solution, but it must be 0 at these 2 points. So it may be like this, it may be like this, or it may be just like this. So all these waves are sine waves. Sine waves. As a result, we get just a sine, but no cosine term here. We can see. So this is a uh, linear solution. This is a linear solution. Okay, this is a linear solution. In this way, we can visualize the problem itself. Hello everyone. Let's do another boundary value problem, and this is von Neumann boundary conditions, and uh, it looks like this. We have a second order ordinary differential equation with two conditions. Now, if you notice here, these two conditions also involve a derivative, first derivative themselves. That's why it is different from the Dirichlet problems that we have seen earlier. Now, let's try to find out the solutions, all the solutions of this question. Now, again, as we did earlier in the Dirichlet problem, let's try to find out all the solutions of these by considering all the cases where lambda is equals to 0, minus or negative, or and plus. Okay, it means, so let's take the first case first, that is lambda is equals to 0. And if lambda is equals to 0, it means that the question becomes y double dash is equals to 0, right? And if this y double dash is equals to 0, then we can say this yx can be any linear function. Okay, so this is a solution, first solution, when lambda is equals to 0. Okay, now let's take another case where lambda is equals to omega square, which is always greater than 0. Then our question becomes y double dash is equals to omega square y. Now, since it's always positive, if we take it to the left hand side, it becomes y double dash minus y squared y 0. So let's try to find out the solution of these, solution of this differential equation. Then we get m squared minus omega squared equals 0. That gives us m squared equals omega squared, and that gives us m equals plus minus omega. This is a solution. These are the two solutions, two distinct solutions, right? So it means we get solutions as e to the power omega x plus b e to the power minus omega x. But the value of this kind of solution is very hard to find if if x here is not equal to 0. So that's why let's explore some interrelationship or relationship between trigonometric function and exponential, and write this in hyperbolic functions of sine and cos. That gives us y of x is equals to a cos of h omega x plus b sine of h omega x. This is second solution. Now, if we apply uh, the boundary conditions there, we can get another solution of the boundary problem. But let's find out the solutions first of all those three cases. So let's take a third condition. Let's take a third condition. Then the third condition here is lambda is equal to omega square, but it's negative. So if it is negative, then our solution or our differential equation becomes omega square y, and this is negative. If it is negative, if it goes there, it becomes positive. Omega square y equals 0, and we get m equals plus minus omega I. So this is a solution. If this is a solution, then our solution to the differential equation becomes, since it involves iota, it is a cos of x plus of omega x plus b sine of omega x. Please notice we have a hyperbolic function when it has positive root, and we have real root, and we have non-hyperbolic trigonometric functions when we have iota or imaginary roots. Okay, now this is the third solution of the third case of lambda. Now let's use boundary conditions in each of them to find out all the solution of boundary value problem. Okay, up to now we have just found out the solution of differential equation in different cases of lambda. So okay, let's try to find out the solution using this set of boundaries. So at x equals 0, at x equals 0, the solution is 0 equals a x is 0, so b is equals to 0. It means that we can get solutions here like okay, so after that we get y of x equals ax, and again get x equals pi, y pi is 0 equals a pi plus b is already 0, so it means pi cannot be 0, so a must be 0, right? That's why we can say if a is equals to 0, then the solution y of x is equals to 0. And if a is not equals to 0, if a is not equals to 0, that means we are compelled to say pi is equals to 0. That means there are no solutions at all. No solutions. So, no solutions. Okay, this is it. So these are the two solutions, or one is for zero solution and another one is no solution that we get for uh, this solution of the differential equation. Now we don't need this. Now let's use the second solution of differential equation to find out the solution of the boundary value problem. So y of x equals a cos of h omega x plus b sine of h omega x. Now it acts. Oh, I'm sorry for that. I'm sorry for that terrible mistake there. Actually, what I had to do is, I'm very sorry for that. Okay. Actually, what we had to do here is, so what we have to do here is, y dash of x is equals a, because the first derivative, the conditions here are not in the original yx form, but are in the first derivative of yx forms, right? That's why we can write y dash of x equals a, and then after, since there are no variables at all, even if we use y dash of x, y dash of, okay, so it x equals 0, then we get x 0 equals a, there is nothing we can do, and 0 equals a. So this says there is no solutions at all. There is no solutions, so we don't need to bother about it, because if a is not equal to 0, okay, if a is not equal to 0, then there's no solution, and if and or we can just say a equals 0, that means y dash of x, y dash of 0, so this is also a solution, so y dash of x is already a solution. This is what we get from the first solution of differential equation when lambda is equals to 0. Now if lambda is positive, then we get the solution. Again, let's find out the solution of it, or let's find out the first differentiation of it. It gives us a sine of h omega x plus omega b sine, sorry, cos of h omega x. This is what we get. Now let's use the boundary conditions there. Then we get it x equals 0, y dash of 0 equals omega a sine of h omega 0, that is sine 0, plus omega b cos h omega 0. Okay, so this is what we get, and at x equals pi, y dash of pi is also 0, is equal to omega. So yep, omega a sine of h omega pi plus omega b cos of h omega pi. Now, since sine h 0 or sine 0 is same, so sine 0 is 0, so we get this is also 0, so 0 equals omega b cos 0 is 1 omega b, and if we consider omega is not equals to 0, if omega is not equals to 0, then it means b must be equals to 0. Okay, so this says us that if omega is not equal to 0, then b is equals to 0, and if b is equals to 0, then we get x equals omega a sine of h omega x. Okay, so we get that solution. After that, let's so from here what we get is cos of pi. Cos of pi is 0, and this sine cos h of cos h omega pi is 0, and omega is sine omega pi, sine h omega pi uh, gives us the value that okay, so wait a second. Okay, I think you have got confused here. Just don't get confused, just understand. I'm going to repeat it again. Okay, just listen to what I say. So what we did earlier was we tried to find out the solution of the second order differential equation for different values of lambda. The first case was lambda equals 0. The second case was lambda equals positive. So we write it as a square of something, that is omega squared, and we consider that omega squared is always positive, and at that condition we got the solution of that differential equation to be this cos and sinh kind of solutions, which involves that say cost and sinh. And after that, what we did is we considered lambda to have negative values. That means we have considered omega squared to be smaller than 0. That means negative. And if we do so, and when we do so, we get the solution, which looks like this. So yx equals omega a sorry equals a cos of x plus b sine of x. Right now, these three are the solutions of the differential equations. But we need to find out the solutions of boundary value problems, right? So that's why now we are going to put those boundaries in these three solutions and try to find out what the solutions looks like. Okay, so what we did first was we differentiated the y x, and by that, and why did we do that? We did that because we have these boundaries in terms of first differentiations or first derivatives. That's why we did first derivative of this yx, and that gives us just a constant of this linear function when lambda is equals to 0. Lambda is equals to 0, right? Okay, so we found out that value, and after that, so we found out that value. Now we have been given that at x equals 0, this thing is 0. That means at x equals 0, y dash of 0 equals 0. So that's why a equals 0. This is a solution. And if a is not equal to 0, then there are no solutions at all. That is the first boundary. So first solution of the boundary condition. Now for lambda is equals to positive, we have got this. We have got this, right? So we also found out the first derivative of that, and we get y dash of x equals this. Now at x equals 0, it is also 0. So that means if at x equals 0, this whole thing is 0. And sine of h of 0 is again 0. That means we get omega b, and cos 0 is 1. So it means omega b equals 0. Now omega cannot be 0 because we have already considered that omega to be greater than 0, right? That's why we get b equals 0 here. Now if we substitute this b equals 0 in here, we get y dash of x equals omega a sine of h omega x. Now again, the boundary itself has already told us that at x equals 0, at x equals 0, at x equals 0, the thing y dash of 0 is also 0. It means this whole thing is 0, but it doesn't mean that this and these are 0, because we have already said this is greater than 0, so a must be 0. And if we substitute this value to there, then we get y dash of x equals 0. So it means that 0 is equal to 0, because it has already given 0 from the differential equation, sorry, from the boundary. That means 0 equals 0 means infinitely many solutions. Infinitely many solutions. Okay, up to now we have done two cases of lambda. Now let's take the solution of lambda smaller than 0. That means it's negative. The solution we get from that condition, that case, is this one. Now let's again use those boundary conditions here. Now at x equals, so first of all we have to differentiate it first one time. That gives us a sine of x minus plus b cos of x. Now we have to use this one, and the boundary condition is at x equals 0. If x equals 0, we have at x equals 0, whole thing is equals to 0. So it means 0 equals now okay, minus a sine 0 plus b cos 0. Now what is sine 0? Sine 0 is 0. Cos 0 is 1. That means b equals 0. If I substitute b equals 0, we get this. Now at x equals pi, the thing is 0. So y dash of pi is 0. It means 0 is equals to minus a sine of pi. Now sine of pi times minus of a is equals to 0. We can remove this minus sign, it goes there, and 0 plus 0 and minus 0 both are the same thing. Now, if a is equals to 0 here, the whole thing would be 0, but the sine pi is equals to 0. It means that, oh, I'm sorry, we have sine omega there, right? So omega x, it means sine omega pi. Now sine omega pi equals 0. Now what are the conditions when sine is 0? It means when does the sine touch the x-axis? The values are, sorry, not touches the x-axis, but it means when the sine is 0. The sine is 0 at pi, 2 pi, and so on, right? That's why we get the value n pi, sine n pi here. As a result of which, we have already considered a not to be 0, so it may be anything. We don't really care about it too much. So we get n pi equals omega pi. So n is equals to omega. This means that we have got sine of nx. A can be anything, so we can write not only the negative but positive or anything else. So that means this is equals to what? Say this is equals to 0. So this is a solution of the boundary value problem. Now let's write whole set of solutions. Now what are the solutions that we got? So we got lambda, which was equals to omega square, is lambda is equals to n square, because we have found omega is equals to n. This is a solution, and it says yx is equals to what? A n of cos of nx, right? Cos of nx. All right. Why? Because now you may wonder why we did this, why we write cos instead of sine, because that was the derivative case. If you remember, that was the derivative case, and if we integrate that, we get this thing, and so this is what we get for our solution of the boundary value problem. Now, if we want to visualize this, we may see in this way. So see it in this way. So at x equals 0 and x equals uh, at x equals pi. Now it says that the boundary value problem starts at first derivative 0. It means first derivative 0 means it is at the steady state or equilibrium, right? Equilibrium. So we can say it starts with this point, and it goes to the pi, and it is again the steady state. It means it it may go like this, like this, or like this. It may be anything, or just like, okay, it may go like this. So these are the solutions that are possible, and all the other frequencies are also, all other harmonics are also possible, in both in the positive as well as negative direction. So these are some graph that may show how that may visualize you, that may help you to visualize the question itself. Okay, so this is how you find the boundary value uh, solutions of the von Neumann boundary condition problem, and I hope this helped you to understand it better. I'm sorry if I made some mistakes and if I got you into any confusion. I hope I I was able to clear those doubts that you had before watching this video. So thank you so much for watching this video. Mm. Up to now, we have discussed about different boundary conditions and other boundary conditions and other things. Now let's directly go into solving partial differential equations. Uh, now, by partial differential equations, I am not considering a lot of partial differential equations. I'm just considering some partial differential equations. For example, wave equation, heat equation, and Laplace equation. And we are going to use the von Neumann and Dirichlet boundaries to these problems to find out the solutions. Okay. Now it would be a very a, a classroom like lecture. That's why you won't get much of editing here. I'm going to keep it as it is, and it is going to be long. So if you could bear it, let's go. Now, okay, now let's talk about partial differential equations. Up to now, we have been discussing the various differential equations which only included only one parameter as an independent parameter. Now, from now, we will get a lot of uh, parameters as independent parameters. So let's start with two parameters, two independent parameters. So if we have uh, u xt is a two variable function, then a PDE involving u, x, and t, and the partial derivative of u is called partial differential equation or PDE. Now, the ordinary differential equations have a unifying theory of existence and uniqueness of the solutions, but PDE doesn't have such kind of theory. So that's why PDEs arise from physical phenomena and modeling. Now, is a PDE can be used in modeling, and it can be used to explain the movements or the motions in our surrounding. It is a very important, and it is a very popular topic of research, mathematical research as well. Okay, so now what else is there to learn about PDEs? Now, if we consider a simple one-dimensional PDE such as heat equation, then let's consider a bar. Okay, we have considered a bar of length L, and it is insulated along its interior. It means we have covered with some insulating barrier so that heat does not flow through its body. It means we are just trying to move this heat from one point to another point. It means in one dimension, and I am not going to give it any room to go to its any other to go heat in any other dimensions. So that's why this becomes simple one-dimensional heat equation. One dimensional. Now, the heat equation of this kind of setup is given by rho x sigma x del u by del t, where del is partial derivative term, is equals to del by del x kappa x del u by del t, sorry, del u by del x. This is going to be the heat equation of this setup, where u xt is the temperature of the bar at position x at time t. Rho x is density of bar at position x at position x. This sigma x is specific heat at position p at position x, and this kappa kx is thermal conductivity at position x. Now we will assume that the bar is uniform. It means that these quantities sigma, rho, and kappa all are uniform or all are constant. In that case, we will get a heat equation which looks like del u by del t equals del square u by del x squared. This is a heat equation that we get when sigma x, rho x, this is rho x, this is sigma x, and kappa x are considered constant. This is our one-dimensional heat equation, or heat, no, or we can say one-dimensional uh, partial differential equation. After that, now, okay, we may introduce a constant in front of it, like c squared, to keep account of these all constants. So what it did is I divided kappa x by the product of uh, these two terms, and I gave it a name c squared. And now this c squared, being one constant, will keep account of all other constants. So our equation, so this heat equation, the original heat equation looks a little bit not messier. Now, okay, so After this, now, okay, if you want to find this c squared, you can find it by this expression, which is just a trivial thing. For the sense of completeness, I just told you that. Okay. Now let's directly jump into problem and understand how do we apply the Dirichlet and von Neumann problems, boundary problems in this kind of heat equations. Okay. So this is our question. Solve the following initial slash boundary value problem, and we have got this heat equation, and these are the initial and boundary conditions. So first one, this one is a boundary condition, and this is the initial value problem condition. Initial value problem. Now it says that if we want to visualize this, you can see here. So we have a rod, and at x equals 0, at the position at the first end, the value of heat is 0, and at the boundary, at the both ends of the rod, the value is 0. It means the heat is 0. And this initial value says that at t equals 0, the initial amount of heat is given by x times pi minus x. And after, as the time goes on increasing, this the value of heat or temperature that was there in the rod gradually decreases over time, and at t tends to infinity, it goes right up to 0, or we can say the temperature becomes 0. Okay, or we can say the temperature settle down to the surrounding temperature. We can understand it, or we can visualize this in this way. Now let's see the mathematical solution. So let here solution, let u xt be temperature of bar at position x in time t. Then our intuition is, when time tends to infinity, the temperature fades away and become equal to 0 or equal to the surrounding condition or surrounding temperature. Now that we can say to be a steady state solution. Steady state solution, right? Okay, this we can say to be steady state solution. So steady state solution means when time tends to infinity, or t becomes very long or very large, then what is the equilibrium position that this system wants to attain to, and this is what we call as the steady state. S stands for steady state solution. Now after this, okay, so after this, our in any questions involving heat equations, or any questions involving such kind of problems, we assume solution to be u xt equals two functions. One function is of x, and one function is of t. That gives us function of x and function of t, and we assume this to be separated, or we use a solving method of separation of variables to solve this two variable differential equation, or two different functions of different parameters. Okay, I mean to say that, so we assume solution to be u xt equals two solutions, one of f, one of x, and one of t, and we just consider these to be a separated, be variable separated. Okay, I don't know how to say it, but you will get that in just a moment. Now this is what we consider the solution to be. In any question we can consider this, we always consider this. Then after that, we will try to find out uh, the partial derivative of t, and second order partial derivative of x here, and for that we get u t equals, we get f dash of x, f of x, z dash of t, and u x equals f dash of x gt, and again u x x means second order partial derivative of x, function of x, and gt. Okay, now this is what we get. Now let's substitute it to the question. Then we get f of x g dash t equals f, sorry, c squared, then after f of double dash of x gt. Now let's separate the variables. It means, let's separate the variables. It means f of x psi f double dash of x equals c squared gt g dash of t. Okay, we get a second order differential term, and a first order differential term in the denominator. Now, what can we do? So after doing that, okay, so we have got this right. Then after, okay, now let's remodify it a little bit. So we get f double dash of x by f of x equals, it goes there, it goes there, it goes there, and we get c squared gt. Okay, now let's consider this to be lambda. This is a intermediate point, a junction point, and this equation right here is called eigenvalue equation. And this value is called, or this function is called, this equation is called eigenvalue equation. Now, what we can do here is, I'm going to separate these equations, and I'm going to get two ordinary differential equations from the original one partial differential equation. We get this, and we get f double dash of x equals lambda f of x. Okay, so these are the two ordinary differential equations. What after that? Now we have got two different ordinary differential equations, but one thing we are missing here is we need some boundaries to solve these problems. And to find these boundaries, now you may wonder, we have got the boundaries right there, right? No, these boundaries are for the function u, which was a partial differential equation, but we have got two ordinary differential equations. We haven't got any boundaries for them. Now we can find out those boundaries in this way. So what we can do is uh, we are going to use these boundary conditions in there, and then we get the values. Okay, now for example, if we have boundary conditions 0t, right? So u 0t equals f of 0 plus f of 0 plus g of t, sorry, not but multiplied. Okay, this, now we have been given that this is equal to 0. It means that f of 0 times gt is equal to 0. Now f of 0 means some value, some constant value, and gt is a function. Now gt function cannot be 0 because we know function cannot be 0, and and it is a time. Okay, so it is okay. It is a function of time. It means that curve is not 0. The curve exists. That's why this cannot be 0. So this function will be 0. Then f of 0 is equal to 0. Again, if we use the second condition, equals f of pi into gt equals 0. Again, this function is not 0. It is f of pi that is equal to 0. We have got the boundary conditions as well. So we haven't got boundary condition for this. We have got boundary condition for this. This ordinary differential equation, and these are written here. Now, so we have got everything that we need. Now let's use the boundary condition and find out the solution. Okay, so after this, if you remember our previous classes, and if you especially remember the Dirichlet problem, then you would notice that this is the Dirichlet problem itself. So if we have seen in the Dirichlet boundary condition, if we have this kind of questions and these boundaries, then we can write the value of lambda to be minus n squared, and the solution, or the all solutions of such kind of question, is just bn times sine of nx, right? Then we have got the solutions of it. We don't need to do nothing from here, from this ordinary differential equation. Similarly, now this differential equation, we need to solve it and find out the solution as well. And we are going to put that solution in there, and we get the solution itself. Okay, now to find the solution of this differential equation, now this is a first order ODE, right? That's why we can use integration factor to find out the value. And if I do so, first what I did is I it is not necessary to do, but I considered this to be y rather than z, and then I found out the value of y, and I just replaced that y with t yg, and I replaced the independent variable of x by t, as we had in this our problem. Okay, now so we have got f of x and g of t. Now let's substitute it in our original solution, and let's get the solution. So I'm going to just rub it out here. So we get u u. Now we have got, so if you see here, we have got n. It means n can be anything from 0, 1, 2, 3, 4, etc. So we have got the solution for nth case only. We have to solve it for all the so okay, one thing I should tell you right now, and it is very important to tell it to understand these things better, is we have assuming that ux is fxgt is a solution. Okay, now it means it is not the only solutions. It means one of the solution. Okay, it doesn't mean this is only one solution. It says that there are a lot of other solutions which are in such format. Okay, in such way. Okay, this is what it means. Now, so that's where this n comes from. So it better explains the n here. Okay, now if we substitute it here, f of u of xt sine of pn. Okay, let's merge this pn and c as a whole, as a single constant, and let's say that to be suppose let's say that to be a right now. Okay, so let's that supposed to be a, and sine of nx now e to the power minus c square n square t. Okay, now since I have already said that this is not the only one solution, this is one of the solution. That's why I can say from the superimposition we can add all the solutions like these that exist, and for that we need to add a summation sign, uh, like this summation n equals 1 to infinity. No matter how many solutions of these forms are there, it accounts for all a sine of nx e to the power minus c square n square t. Okay, and okay, so this is what the solution, or we can say this is a general solution of this bound initial slash boundary value problem. Now you can see here, we are saying this to be general solution. What about the particular solution? Okay, to explain that, we need to see the boundary itself. If we have anything else than zero here, then in that condition we say that to be a particular value problem, and we have to find out the particular solution as well as a homogeneous solution. So we would separate the two and find out the solution. Now this is a homogeneous solution. Okay, so the homogeneous boundary and homogeneous boundary problem, and in those cases we don't need to find out the particular solution because the particular solution doesn't exist, and that's why I'm just saying it this to be general solution without adding any particular solution to it. This is actually the homogeneous solution as well as the general solution. That is what I want to mean. Okay, now this is what the solution, the solution of this heat one dimensional heat equation is. Now we have used everything here, but we haven't used the initial value problem yet. That means our job is not quite finished yet. We need to use this initial value problem too. Okay, so for that, let's plug t equals 0, and we get the value. So u 0t equals summation n equals 1 to infinity a sine of nx and e to the power minus c square n square 0. It gives us value 1, and this is equal to x by minus x. Okay. Okay. Now here we need to compute Fourier series. Now which Fourier series, Fourier series among sine series and cosine series we would like to find out, or we want to find out. So we need to find Fourier series. Now if you remember our Fourier series formula, it was f of x equals a naught by 2 plus summation n equals 1 to infinity a n cos of nx plus bn sine of nx, right? Now for cosine series, sorry for that. So now for cosine series, Bn was equals to 0. And if b1 is equals to 0, then we get f of x where a naught by 2 exists plus summation n equals 1 to infinity a n cos of nx. And I'm not going to say or talk about how do we find the a n and everything. I'm just talking about the general thing here. Now, if we want to find out the sine series, it means that a naught is equals to 0 and a n equals to 0. That gives us just the sine term. Sine term, it means okay, this, then after bn sine of nx, right? Now if you see this one and if you see this one, these two looks very similar, right? That means here first we need to find out the Fourier series, Fourier sine series, then we can compare it to find the value of x, find the value of a. Okay, so let's do that. So to find out the Fourier series, we have got this formula to guide us. Now we have to understand just a single thing, and that is how we find the Bn. Now Bn is equals to 1 by L minus L to L of f of x times sine of x sine of n n wait a second n pi L x dx. This is how we find Bn. Now, what is our solution? What is our function? Now, the function is f of x equals x pi minus x. If you don't know, this is a parabola. This is a parabola like this. Okay. Now, if you want to find out the sine series, then it goes sine series. It means we have to find out. So we have to make it periodic along or symmetric along origin, and we need to make it periodic in this way. Okay, if you do so, then we can write L is equals to 2L equals 2 pi, L equals pi. 2 pi is the periodic, 2 pi is the period for this wave. So we get 1 by pi minus pi to pi, f of x is x, pi minus x, sine of n pi by pi, x dx, these pi and pi are cancelled, so we get sine nx. Now after this, 1 by pi, what we can write is 1 by pi, okay, so 1 by pi integration minus pi to pi x pi x sine of nx minus x squared sine of nx dx, right? Now, if we solve this, I'm not going to solve this because it is going to be very messy here. If you solve this, you would get something like this. So Bn equals 4 1 minus 1 to the power n by n cubed pi. This is what we get for the value of Bn. Okay, now it means that this Bn, we have to write the value of this Bn to be this thing here, this creature. So f of x equals summation n equals 1 to infinity 4 1 minus 1 to the power n by n cubed pi times sine of nx. It doesn't matter if you can't see up to here. I'm going to write it down there too. So okay, so if you compare this f of x and this u0t, if you say u0t is equals f of x, then it must be equal to, and it implies that bn is equals to a is equals to 4 1 minus 1 to the power n by n cube pi. Okay, okay. So if you say so, then the final series that we are going to get involve, so final solution of uh, this one-dimensional heat problem is u n x t is equals to summation n equals 1 to infinity. A is 4 1 minus 1 to the power n n cube pi times sine of nx e to the power minus c square n square t. This is what the actual solution of this looks like. So this was heat equation, one dimensional heat equation. It wasn't that bad, was it? Okay. Thank you so much for this. Oh, okay. I just remembered something. Uh, Now, what would you do if those boundaries were inhomogeneous? So it means we have got something. We have got this problem like this. Now, how do you solve this problem? So to solve this problem, first of all, we need to consider this, or we need to suppose a function which is equals to this. Then that function is a homogeneous function, and we will try to solve that by using the following the previous method, and then we can add 32 after the general function is a particular solution, and in this way we get solution of such kind of problems. Let's see how it is done. Now let's so what I said is, in solution we consider a function which is two-dimensional function, which is a function with two independent parameters, and these to be equal to u of xt minus 32. That means v of 0t is now u0t minus 32, and v of pi t is equals to u pi t minus 32. In this way, again, this x0 becomes v x0 equals x pi minus x only, because plus 32 and minus 2 minus 32 cancel each other. After this, our this question also get modified, and our question now becomes v t equals ut, and vxx becomes uxx. So that gives us the solution. That gives us this question modified is c square vxx. This is our new question. Okay. Now after doing this, we know that the solution vt, what we got, is actually same as what we got in the previous case. For example, if we say the v, if we write v and t is equals summation n equals 0 to infinity 4 1 minus 1 to the power n cube by sine of nx e to the power minus c square n square x. This is what? This is a solution of vxt. This is the solution of vxt, right? Now we have considered vxt to be uxt minus 32. So to find out uxt, we have to shift that minus 32 towards the left hand side, and that becomes plus 32, right? That means if we want to find the value of umxt, it is summation n equals 0 infinity 4 1 minus 1 to the power n by n cube pi sine of nx e to the power minus c square n square x plus 32. This minus 32 goes there and becomes plus 32. You can understand this as in this way too. So you can understand it like this. So this is a homogeneous solution. Okay, so you can okay, so n and is h. Okay, this is homogeneous solution. This can be understood as homogeneous solution, and this can be understood as particular solution of xt. In this way we find out the solution for the inhomogeneous boundary conditions as well. So I hope I covered everything. Now in the next video we will talk about the von Neumann's condition, von Neumann's boundary, and we will going to repeat this process, uh, and we will do everything that we did right now. Okay, so thank you so much for watching this. So hello again, let's do some questions. Actually it is a continuation of the video. The problem that we were doing on the boundary problems, the one-dimensional heat equation. Now let's use von Neumann's boundary condition in this one-dimensional heat problem to see what kind of solution do we get. So okay, before that, uh, at the last of previous video, we talked about the steady state solutions, right? So what is the steady state solution? Now, okay, so so to understand this steady state solution, we need to understand the general overall idea of the solution itself. So what is the solution and how do we solve? Now to solve the initial boundary value problem means to solve the first to first solve the related homogeneous solution, and then steady state solution, which is given by u as xt is equal to a plus b minus a by pi times x. So this is what the steady state solution is. Okay, now we use this formula to find out the steady state solution. Now we will see a question, and this would be more clear. So von Neumann boundary conditions. So let's write the question. So here we are with our question. Now we can see that this is a homogeneous solution. This is a homogeneous boundary conditions, and we have initial value condition here. Now let's say uxt stand for the temperature of bar at position x and time t, at any time t. Then let's assume that we have a solution in the form of uxt equals f of x and g. Actually, now I want to write it in capital form, capital G I, capital ZT, in this way. Now let's play with it again. So what we do is, we try to find out t equals f of x g hash t u of x equals capital X double derivative of x plus actually second order derivative of x, not plus, it's product. That's why zt. Now okay, so let's substitute these, and after substituting this we get so we want to substitute this in this, so I substitute, and after substituting we get substituting in original equation we get f of x g dash of t equals c square f double dash of x and gt, and we get f double dash of x by f of x equals g dash of t by c square gt. Let this to be lambda. Then we get two ordinary differential equation. First one looks like this, the second one looks like this. So this is our solution. Okay, if we sorry, these are our ordinary differential equations. So what next? So we have got our ordinary differential equations from partial differential equations, but we haven't got any kind of boundaries. So for that, let's find the boundaries. And to find the boundaries, we have to find out ux of xt, that is ux of xt, that is f dash of x gt. Now this ux of 0t is equals to f dash of 0 gt, and ux of x0 equals f dash, so f dash of 0, so f dash, wait a second, I think it's pi. Let me check the question, and of course it's pi t, and phi t gives us pi gt. Now here we can see this is a function that defines the temperature. That means if we try to draw a temperature profile, then we get something like this. It means we had at x equals 0, there is a so at x equals 0 the temperature is 0, defined by initial condition. Actually it's not the curve does not look like this. Actually it looks something like this. Okay, by it looks something like this. I mean to say that if you see here, this is a differential sign. If differential is 0, that the first differential is 0, it means that it is in the steady state solution, or it's a constant, or it is stable there. It is constant there, right? That's why it is constant there at x equals 0. Yeah, so I should by that. Again at x equals pi, it is again constant. So this is a function. Okay, now this function is defined by zt. This function changes according to time. Okay, according to or is for time. along the time it changes. That's why z cannot be 0. This is a function. Function cannot be 0 here because it defines a curve. That's why these values, f dash of 0 is a value, f dash of pi is value. These need to become 0 to make these left hand side 0 defined by boundary conditions. That's why we get these boundaries, and these boundaries are for f. That's why we get a von Neumann problem. Von Neumann problem. F double dash of x minus lambda. F double dash of x minus lambda. F of x equals 0. This is the differential equation, and we get boundary f dash of 0 equals f dash of pi equals 0. So now what we are going to do is we are going to use the von Neumann's condition and find out the solution of it. Now I'm not going to write that again, so I'm going to revisit my solution there in the previous video, and I'm going to write its solution. So previously we have got lambda equals minus n squared and f n of x equals cos of nx. So we have got this. Now let's substitute this in this equation. Then we get something like, okay, so before doing that, let's find out the solution of this first order differential equation as well. And we get that c dash of t minus and minus will be plus, lambda is n squared c squared gt equals 0. Now this is a first order differential equation with px with, so if you consider this to be gt plus p of t times gt, then p times t is equals to n squared c squared, and from here we can find out integrating factor, and integrating factor is given by exponential power p dt, and it gives us e exponential and n squared c squared t. Again it gives us e c squared n squared t, right? I hope you can see that. Okay, after finding that we get, I'm going to write it here, okay, I'm going to write the solution of it, and the solution is given by g of t equals g of t times integrating factor, that is e c squared n squared t is equals to 0. That is a constant because integration of 0 is constant. I hope you understand this because this is a very trivial thing. It's just a first order differential equation. You can solve it by using that integrating factor method, and you can get solution. I'm not going to waste my time here, and I'm going to just simply write the solution, which is this. So this is the solution of this differential equation. This is the solution of this differential equation. So this is what we get from here. This is what we get from here. Now we have already assume that the solution looks like this. Now let's substitute these and let's see what the solutions looks like. So the u xt equals c times, let's suppose a constant here, let's suppose an times c, let's just suppose this to be a, okay. Now a times c is some constant, I don't know what it is, let's say b of cos of nx times e to the power minus c square n square t. Now this is the solution. Now this solution makes sense because this cos of nx is cos of nx shows this curve, okay, and e to the power minus c square n square t means along with time this heat or this temperature is going to fade away or be equal to the surrounding, okay, and that is what this e to the power minus term is representing here, because it is a kind of it is a term that is involving the damping in the solution. So now we have found out the solution. Now is it the only solution? Oh, sorry, it is the only solution. Is it the only solution? I have already said you, we have assumed that the solution is of this form, and it is not the only one solution, that is just one of the solution. That's why we can use summation to account for whole solutions, all the solutions that are there. And that means what I can do is I can say un of xt is equals to summation n equals 0. Okay, now suppose n equals 0, so n equals 1 to infinity, and this b of cos of nx. So this why this summation sign is here? It is holding the count of every other solutions of this nature possible. Okay, that is what the summation is representing here. Now this is what we get as a general solution. General solution. Now this problem doesn't need to find out any kind of particular solution because the boundary condition are homogeneous itself themselves. That's why we don't need to find out any particular solution here. But we need to do something else, which is to use initial value problems. We haven't used initial value problems. We have just used boundary value problems up to now. Now let's use this initial value problems. Now how do we do it? So the solution here doesn't account for this. Now for that, actually this is okay. So okay. I need to rub this all, and I'm going to write it again. Okay. So this is what we are going to work with. Now let's see. This looks like a Fourier series, but it's not completed, and we can find out the uh, what is it called? The Fourier series of this function. So this is essentially a question that says find out the Fourier series of this function. So this is a question which says we have to find out the Fourier series of this, and from that we are going to find out the value of b constant here, and then only we can write that to be the general solution, which also account for the initial value problem. Now for that we need to find out the Fourier series of this formula, and okay, and now we can do that, but let's use our intuition here and make our things a little bit more easy. So less complicated. So what I mean to say is that, so we have this right now. If you remember sine series, to find the sine series sorry for that. Now we need to consider a not to be 0, and we need to consider a n to be 0, right? And the Fourier series is given by a naught by 2 plus summation n equals 1 to infinity a n cos of nx plus b n sine of nx. Now, if you see here, we have a cos term, so we cannot say a n is 0. That means we are not going to find out sine series. Rather, we are going to find cosine series, cosine Fourier series. That means we are going to allow this bn to be 0, and this an can be found by 1 by L minus L to L f of x times sine of nx dx in this way. Sorry, cos of nx dx, and a naught equals 1 by L minus L to L f of x. Cos 0 is 1 into dx. That gives us 1 by pi minus pi to pi x pi minus x into dx. Now we need to find the solution of this, and just to do that, 1 by pi minus pi to pi x pi dx minus 1 by pi minus pi to pi x squared dx. That gives us 1 by pi is common, minus pi, actually let's set this to be this, and minus pi to pi minus 1 by pi x cubed pi 3 minus pi to pi. That means we have this and this are cancelled, and pi whole squared by 2 minus pi by 2, this gives us 0, minus 1 by pi cube by 3 minus pi cube by 3. That gives us, this is 0, right? Because this would be plus, and the same thing cancelled. Minus 1 by pi cube by 3, and minus is plus. This gives us minus pi cube by 3. That gives us, okay, that gives us 1 by pi minus 1 by pi. Okay, wait a second. I'm going to take minus pi cube by 3 as common. I'm going to get plus 1. That gives us minus pi cube by 3. Pi plus 1 by pi. That gives us a naught is equals to minus pi square by 3 pi plus 1. This is what we get for pi for a naught. I don't know. I made a mistake or something. But actually, this a naught must be minus wait pi square by 3. I don't know what I did here. I think I made some mistake. Please check. It must be pi square by 3. Okay. Now let's find a n. I'm sorry for that mistake. So okay. So a n 1 by L minus L to L. What is that actually? X pi minus x cos of nx dx. L is minus pi to pi. This is pi. Now this is 1 by pi minus pi to pi of x of cos of nx dx plus okay, can we do that? I don't think we can do that. Okay, so how to solve this? To solve this, so I'm not going to solve this. I'm tired of solving such kind of questions. I'm going to just write it. Okay, I'm just going to write the solution, that is 2 1 minus 1 to the power n by n squared. Okay, this is what we get in place of an. Now this an must be equal. So from an we can say fx equals pi squared by 6, because a naught by 2, right? So 3 times 2 is 6, plus summation n equals 1 to infinity. This thing right here, an, and cos of nx must be equal to u and so u h. It's not n, this is n, so u n xt. That gives us, now we that says is that we need to write pi squared 6 in front of this. Okay, a naught pi squared 6, and in place of b we need to write the thing an. And after doing that, after writing pi squared plus 6, after adding this, and 2 1 minus 1 to the power n by n squared, this is what the general solution is, with account for all boundary as well as initial value problems. This is general solution. Okay, this is general solution. Now, so this is it. This is general solution. Now, so I have already told you how to solve the the uh, particular solution as well, right? In the Dirichlet boundary condition problem. So that's why that's it. I hope I made it clear. Thank you so much.